Hello friends. Uh, so today we are going to see the subject of mechanics of solid. So out of that, so mechanics of solid, in the previous lecture we have seen different types of material, classification of material and mechanical properties of material. So today we'll start with the stress, a term stress. So simple stress. So today we'll see about the simple stress. What is actually simple stress means what? What are the terminologies used in simple stress? What are the equations of simple stresses are there? Okay, so today we'll see this. So the presentation outlines are stress. So actually what we are going to see today is stress, types of stress, strain, types of strain. So actually this types of strain we are going to see in next lecture, and what is the relation between stress and strain we are going to see in today's lecture. Okay, this is the outline of the presentation. So stress means what? So here you can see stress are expressed as the ratio of applied force divided by the resisting area. That is equals to stress. So simply mathematically, it can be elaborate like sigma is equals to force upon area, that is P by A. So here sigma stands for stress, force stands for P stands for force, A stands for the area. Okay, so here you can see body is there, a simple body is there, or you can see a single rectangular section is there. So a P force is applied on the section. P force is applied on the section in a single dimension. In a single dimension means what? In a single axis, on a single axis, on both the opposite way the force is applied. So this is uniaxial force. Okay. So when the force will be applied, if you'll cut the section at x, here you can see there will be the resisting force. Due to this force P, there will be the resisting force here R, and actually due to the force P in the opposite direction, there will be again the resistance force R will be there in the body of the section, in the body. Here, that's why so stress is equals to force upon area. So force is P here and area of the section. So area will get the area of the section. So sigma is equals to force upon area, force per unit area. So actually what is the unit for stress? So actually the Newton per meter square is also called as a Pascal. So Newton per meter square is the unit for stress, that is Pascal. So convergence of this Pascal. So 1 Pascal is equals to 1 Newton per meter square. 1 MPa, that is 1 megapascal, is equals to 1 Newton per mm square. 1 GPa, that is 1 gigapascal, is equals to 10 raised to 3 Newton per mm square. So this is the conversion. So 1 Pascal is equals to 1 Newton per meter square. So here the unit is Pascal, Newton per meter square for the term stress. So we'll see now what is the concept of stress. Consider a member made up of an elastic material having length L. So here consider this member. Okay, so consider the specimen having length L, cross-sectional area as shown in figure. So cross-sectional area here you can see as shown in figure, subjected to tensile force P. So force is applied. Then that is a tensile force because the force is in opposite direction. Force is in opposite direction. So that is nothing but a tensile force we have applied on the body. Tensile force we have applied on the body. So due to the tensile force, the member will try to deform. Yes. What happens when this force is applied on the body? It will try to deform. It will try to elongate. Hence, resistance will be developed by the material to this deformation, which is uniformly distributed over the cross-sectional area XX. Yes. Here you can see in the previous image we have already discussed that due to this force P, the equal force will be applied in the resistance form. The resistance will be applied for this force. Okay, reaction will be applied for this force P for the cross-sectional area at section XX, and it is uniformly distributed over the cross section. It is over the cross section uniformly distributed. So R is the resistance force. R is the resistance force. Similarly, in the opposite direction, here the force is applied. Due to this force, the resistance will be developed here. Due to this force, the resistance will be developed here. Because of the material, it is having some strength. So due to that strength, the resistance will be developed. And for this deformation, actually the deformation, this resistance is there, which is the deformation is due to this force P. So this internal force of resisting against deformation means what? The internal force R of the resistance against the deformation per unit area is known as stress. Per unit area is known as stress. In equilibrium condition, the internal resistance R is equal to the external force P. So when in equilibrium, suppose this section is in equilibrium. In equilibrium condition, this force P will be equals to the resistance force R. Okay, it will be equal. So here sigma stands for stress. Here already we have discussed force by area. Sigma is equals to resisting force R. So when P is equals to R, so resisting force R is divided by cross sectional area A. Since R is equals to P, sigma is equals to R by A, or it can also be written as sigma is equals to P by A. Okay, because R is equals to P, because how much force is there applied externally, that much will be the resistance in the opposite direction. That much will be the resistance in the opposite direction. That is stress. That is stress on that area, on that unit per unit area here. Okay, so this is the concept of stress. Now we'll discuss about types of stresses. The resisting force offered against deformation. The resisting force offered against deformation can be split into normal parallel to the sectional area. Therefore, there are two types of stresses. So one is axial or normal stress. So in axial or normal stress, there are two types. One is tensile stress and second is compressive stress. Okay, so we'll discuss later in detail about the tensile stress and compressive stress. And second one is shear stress. So here, first of all, we'll discuss what is meant by tensile stress. When a body is subjected to two equal and opposite axial pulls P, as shown in figure, also called tensile load, then the stress induced at any section of the body is known as tensile stress. Okay, it acts normal to the area and pulls on the area. Okay, means what? When the stress is developed due to the tensile force. Okay, when the stress is induced in the body due to the tensile force or due to the pull is known as tensile stress. Means what? Suppose you are going to pull the body here in opposite direction by P by in right hand side and P by left hand side. When you are going to pull this body from both the direction, so there will be some elongation, there will be some deformation of the body, due to the force, and due to that force there may be some resistance to the deformation also. Okay, that is nothing but we can say resistance is developed on that area. Is nothing but a stress, and this stress is developed due to the tensile force. That's why we are calling it as a tensile stress. Here you can see sigma T. Sigma T stands for tensile stress. So the body is pulling in both the direction, and stresses are developed in opposite direction on both the forces, and per unit area of that section x. So due to this, that is called as a tensile stress. So here second is compressive stress. So as tensile stress is developed due to the tension force, here what happens when a body is subjected to two equal and opposite axial push P, also called compressive load, then the stress induced at any section of the body is known as compressive stress. So in the previous tensile stress, the body was pulled on opposite side. Here what happens? The body is pushed from both the sides, from opposite sides. So due to this force, push, there may be some resistance again. There may be some resistance. So suppose this force is pushing the body in the right direction. So there will be some opposite. There will be some resistance. There will be some resistance due to the force applied externally. So this force is sigma c. This is the stress per unit area. This is the stress per unit area due to this force. Due to this force. Similarly, in opposite direction, there may be the resistance. There may be the resistance. Okay. So this is about the compressive stress. This is about the compressive stress. So what is the basic difference in tension stress and compressive stress? When the body is pulled, tensile stress is developed. When the body is pushed, compressive stress is developed. Compressive stress is developed. Here you can see. So this is the bar having a length L, capital L, that is original length, and due to the force, due to the tensile force, there is some deformation. There is some deformation delta. There is some deformation or extension delta. Okay, and there may be some reduction in the cross-sectional area also. So this is the original B. B is the original size, and B dash is the deformed size. Deformed the size of the section. Deformed the size of the section. So here you can see the dotted line. Dotted line. So this is due to the tension, and here similarly, original length L, a specimen having original length L is there, and force is applied in compressive way. Okay, it is pushed on opposite side. It is pushed on opposite side. So here this is the original size of the sample, and due to the force applied, external force is applied, there is some deformation. There is some deformation, that is delta. That is delta. Here there will be, as here the cross sectional area decreases, here the cross sectional area has increased. So B is the original size. B by B is the original size, and B dash is the increased size of the section. This is due to compressive load, and this is due to tension load. This is due to tension load. Now next is shear stress. Shear stress. When a body is subjected to two equal and opposite force acting tangentially across the resisting section, as a result of which the body tends to shear off the section, then the stress is induced, which is called as shear stress, and it is denoted by tau. It is denoted by tau. So here you can see the two forces are there, but the two forces are tangential. Tangential forces are there. So consider this is a nut which is connected here for the two plates. Okay, and the upper plate is pulled in left hand side, and the bottom plate is pulled on the right hand side. So due to this pull, here you can see there may be some resistance in the along the axis. There may be some resistance along the axis. Resistance along the across the tangentially across the resisting section. Okay. So this is due to, so here due to this force P, there is some resisting forces there on the upper part, and due to the force P in the bottom plate, there may be some opposite resistance will be there applied. And here the shear you can see. Here the shear you can see. Here you can see the failure of the nut bolt connection. Here you can see the failure of the nut bolt connection. Okay. So this is denoted by tau. So shear stress tau is equals to shear resistance R. So this is the resistance R developed. This is the resistance R developed divided by shear area, which is denoted by A. That is R by A. So shear stress tau is equals to R by A. R by A. So shear stress induced in the member whenever the applied loads causes one section of the body to slide past its adjacent section. In that case only the shear stress is possible. In that case only shear stress is possible. Okay, so this is nothing but shear stress. Shear stress. So one more example I have shown here. So consider a rectangular block here. See, consider a rectangular block A, B, C, and D, having height of the block H and length of the block capital L, and width is equals to unity. So consider 1 meter of the width, unity. So let the bottom face AB, so this face AB of the block be fixed to the surface as shown in figure A. So here you can see in this figure. So AB, part of the block AB is fixed at the bottom surface, which is shown in figure A. Okay, so let the force P be applied tangentially along the top face CD on the block here at the top. So let us apply the force P. This is the force P tangentially to the surface CD of the block. So such a force acting tangentially along the surface is known as shear force. So this force is shear force. For the equilibrium of the block, surface AB will offer a tangential reaction P. So here you can see. So to get equilibrium, to come in equilibrium, so this due to this force P, the surface AB will apply the tangentially opposite force to come the body in equilibrium. Come the body in equilibrium, that is P, equal and opposite to the applied tangential force P, equal and opposite to the applied tangential force P. Here you can see at the bottom. So resistance is developed. Resistance is developed. So consider a section XX. Consider a section XX here parallel to the applied force. So parallel to the applied force P, which divides the block into two parts. So here you can see the upper part and the lower part, which divides the section into two parts, upper part and lower part. So CDXX and ABXX. Okay, so it is divided into two parts. The upper part will be in equilibrium if P is equals to R. When the upper part will be in equilibrium when P is equals to R, that is resistance force. When applied force will be equals to the resistance force. This is shown in figure B. Here you can see in figure B. Here we can see. Similarly, the lower part will be in equilibrium if the P. Similarly, the lower part will be in equilibrium if P resistance R as shown in figure C. P will be equals to the resistance force R. Okay, so then we can say when the external force is applied to the resistance when the body is in equilibrium. When the body is in equilibrium, which is shown in figure C. So the resistance is known as shear resistance, and the shear resistance per unit area is known as shear stress. Shear stress, which is denoted by tau, which is equals to shear resistance R divided by shear area A, equals to R by A, which is equals to P. So P is equals to R here because the external force is equals to the resistance force. Okay, so we can write down P or R. We can write down. And what is A? A is the area, that is length of the block ABCDL, and the width is the resisting area is the width, that is we have considered unity, that is equals to 1. So that is tau is equals to P by L into 1, that is area is equals to L into unity. So this is the another example for understanding the shear stress. Okay, few images. From the images we can understand what is the stress. So types of stress diagrams. So first is tensional stress. Tensile stress already we have discussed. So what happens in the body when the pull is there? When pull is there, this type of cracks will be developed. These types of cracks, and the deformation will be there. Deformation will be there in the section. So this is the tensional stress or tensile stress. In second image, you can see the compressive stress. So here what happens? The push is there. On both the opposite sides, the body is pushed here. And in third image, you can see tangential force is applied on the two sections parallel to each other. So what happens due to this is shear stress is developed at the axis. From these images also you can understand what are the types of stresses. Now examples of single shear, double shear and punching shear. So now we have understood what is meant by shear stress. Here we'll see what is meant by single shear, double shear. So here two plates are there which is connected by a single nut bolt connection. Single failure plane. So here when the force is applied, so load is applied to the upper plate in the right hand side and to the lower plate to the left hand side. So due to the force applied, what happens here at the center, the nut will be break. Okay, so it is the failure is in single plane. That's why it is called as a single shear failure. Here two plates are there. Here three plates are there. So two plates are forced. The force is applied on the two plates in the same direction. That is 0.5 into load and 0.5. Same load is there. Same loading is there. Upper plate having 0.5 half of the load. Lower plate is having half of the load. Okay, and the central plate is applied load in the opposite direction to the two plates. Here the failure will be in double plane. Two planes will be there. Double failure planes will be there. So the section will be cut into three pieces. Here the section will be cut into two pieces. So here you can say that this is the double shear failure because the plane are two. The failure is in two plane. That's why it is called as a double failure plane. And next is punching shear. So best example in by this image only we can understand what is meant by punching shear. So suppose a slab is there, flat slab is there, and which is resting on a column. So due to the load applied on the slab, if the section is not safe here, the failure will be like this. So here the punching shear will be there. At the area of the periphery of this section. Okay. So this is nothing but a punching shear. So downward load is there on the slab, and the failure will be like this. Okay. It will tear the slab. Due to the force applied on the slab, and equal and opposite force will be there on the column. Upward force will be there. Now Hooke's law states that when a material is loaded within an elastic limit, the stress is proportional to the strain produced by the stress. This means that the ratio of stress to the corresponding strain is a constant within the elastic limit. Okay, in the elastic limit, the ratio of stress to the corresponding strain is constant within the elastic limit. Is nothing but we can say it is the Hooke's law. Within the elastic limit, the ratio of stress applied to strain developed is constant. The constant is known as modulus of elasticity or Young's modulus or elastic modulus. So this is the relationship between stress and strain. So sigma is inversely proportional to strain, or sigma is equals to E into strain. Okay, so here E is the Young's modulus or elastic modulus or modulus of elasticity. So E is equals to stress upon strain. That is P by A is the stress, and original length to the change in length to the original length is the strain. So the denominator will goes up. That's why it will becomes P into L divided by A into delta L. So L is the original length of the section. P is the force applied. A is the cross sectional area, and delta L is the change in length. So this is regarding relationship between stress and strain and Hooke's law. Thank you.